so here's homework 8, problem 1 in dynamics. So we have students from that ES143 class. Was it engineering by design? That's a freshman class. They're always making weird stuff. So here they've made a Rube Goldberg machine, and if you're not familiar with Rube Goldberg, I suggest that you Google him. He's a cartoonist that would make intricate, unnecessarily complicated machines as part of their design project. And block A right here weighs 60 pounds and it's on an incline. It's at 75 degrees and it's got a coefficient of friction of 0.2. And it's attached to block B right here by a rope that don't stretch and a pulley that doesn't get mass or doesn't have any mass or doesn't have any friction. And at this instant that we see right here, block B is moving upward at 0.75 feet per second. We want to find the speed of block A after it has moved down the slope 3 feet. Boom. So here is our setup rewritten out. Now this is a work and energy problem. So what I like to do, one of the very first things, well actually let me take a step back from that. We still need to get the friction force of A. Now because this is a dynamics problem, not a static problem, we will do both an FBD and an IBD because it's the right thing to do, not necessarily because we have to. We don't necessarily have to do the IBD, but I am asking you to do it anyway because it's just the right thing to do, right? So we will make a slanted x prime and y prime slope of A and try to make a little FBD of him. Let's see, a little cheap right there. And here, right, make a box. Make another box. Now you could argue that the IBD isn't necessary here. And sometimes I think maybe I have skipped it, but I think it's the right thing to do to go ahead because it's a dynamics problem, right? We don't want to just shortchange, right? So this will include the little pulley, and this is going to be 2 times the tension. And I guess it's accelerating. This is actually accelerating down that way right there. So here's the mass of A times the acceleration of A, even though we're not going to need it. What we will need is this weight right here. Here's the weight of A. And here's the angle, theta. And this is the whole purpose behind this is we want to get this normal force. And it's sliding downwards, so actually friction is actually coming that way, right there. So we'll go F, and this is actually A. Let's go F, FA, and FNA. So the reason why we did all of this is a little silly, maybe, I don't know. We want to have, I'm going to go positive. We want to get the normal force. We need the normal force. We need the friction force, actually, but we'll get the normal force in this way right here. And like I said, if this was a Newton's second law problem, we would do the first, we would do this y prime, then we would do the x prime. But we're not doing that in this case. We're doing a work energy problem. So in the y prime direction, we're going to have a negative WA times the cosine of theta. Right, and then the only other thing is the FNA, but it's not accelerating in the y prime direction, so it's 0. So we find FNA is going to be 60. So make sure I get this out. 60 times the cosine of 75, which should come out to 15.53 pounds. Yep. And then we can also find, now we can find the friction of FA. This is going to be the coefficient of kinetic friction times FNA, or 0.2 times our 15.53. So not a lot. And I might want to double check my numbers. I think I ran through this already in a separate sheet to check numbers. I think so, somewhere. It was a different problem. There, right there. Yeah, that's it. Okay. So I'm able to look at numbers. So I ran through it in the scratch paper. Okay. So now we have to do our main work energy type of thing. I like to write this out first and then start thinking my way through. And if we learned anything from that recent exam, it's write some stuff down. Like as you're thinking, write things down. And that will definitely help you get points, but also you thinking through your problem. So here's our main equation for work energy. We have the kinetic energy at state 1, the potential energy at state 1, the work, which I'm going to use capital U for, that's done between states 1 and 2, the kinetic energy at state 2, plus the potential energy at state 2. And you could think of this as the energy inventory equations that you might use in thermodynamics or in fluid mechanics. But here we're also using them in dynamics. Okay, so we already know by this that A is going downwards and B is coming upwards. A lot of times I like to have more room than this, but here I'll just draw this kind of as a dashed thing right here. So this is going to be state 1, and this is the location for state 2, right? So this is actually a state 1 datum. A lot of times I'll like to write that. And then I'll also draw, I don't have a lot of room here, so I didn't want to redraw the thing, but I will draw out. Okay, so A has moved down, right? So it doesn't matter. We actually kind of want to go from the center of gravity, but it doesn't really matter as long as we use the same location here. So we'll have this spot and this spot. So this is the location of the bottom corner at state 1, and this is state 2 right there. And for this one, this will be the datum. We don't have to have the same datum for both, and I prefer to do it this way so that the lower of the two is the datum. So for B, this is the datum, right? It starts out of the datum. At A, it ends at the datum. And I do that because I don't like to have negative potential energy, which some books will do. So I prefer to think of potential energy as being always a positive thing. Like here we're about to gain potential energy, here we're about to lose potential energy. So it starts out with potential energy and finishes with none. Here this starts out with no potential energy and ends up with potential energy. Okay, I also probably messed up. I should also have probably done my dependent motion problem, right? So that right there would be like the datum for this thing, right? So, and then I'm going to mark it to like right there. So I'll call this SA, and I'm going to call this, I'm not leaving myself a lot of room here. Maybe I'll cheat right here. I'll write datum underneath this. Datum. Now this is the datum. I'm referring to this is the datum that's for the work energy portion of the problem. Then I could say that these are actually the datums. I don't think you could say that. And this is going to be YB. And don't have a really good place to write this where it's not going to cause a mess. Let me go right here. I'll say 2SA, right, because there's that and that, plus YB is going to be equal to L1, or the only L. Let me take the derivative of this, and we're going to find 2VA plus VB is equal to 0, so we know that that's 0. Something we know that this is going to be true when we go for the velocities. We don't actually need the accelerations in this one because we're not doing Newton's second law. We're not paying attention to acceleration, only velocities and position. Something I wanted to point out here, we might want to have a delta SA and a delta B. That might be confusing because we don't know the length, but we could take the velocity, we could multiply both of these by the same amount, like delta T, and we would get what the delta S, right? So we could also say that sorry about that, 2 times delta SA is going to be equal to the absolute value of delta YB, right? I'm not going to play around with the sign convention game with this. We know one goes up and the other goes down, so that's fine. We're going to need this later on. That's why I'm doing it up here at the top. It's nice to get those kinds of things out of the way. It's also, when we recognize that this is a dependent motion problem, start writing those things out so you get some points for it. So we'll start out with the kinetic energy at state 1. I'm going to say equals. That's going to be, now these both are actually moving, because we know this is moving at state 1, right? We were given that it's moving at 0.75. So that means that actually A is moving downwards at 1/2 of that. So it's actually moving down at 0.375. So we'll write out the equation here. Mass of A times the velocity of A1 squared plus 1/2 mass of B, velocity of B1 squared. And it doesn't matter what direction, whether they're going up or down. Even, you can even think in terms of this way, the velocities are squared, right? So whether there's positive or negative, didn't matter. They just have kinetic energy, so that kinetic energy needs to be you need to pay attention to it. The mass of A is actually going to be the weight of A divided by 32.2. So we're going to take that 60 and divide by 32.2 and multiply by, I'm going to do this in my head. I could write it out somewhere. 1/2, right? Because we know that velocity of A is 2 times velocity of B, so therefore velocity of A is 1/2 the velocity of B. So we'll write that out. I'll even write it out inside here. Go 0.75 divided by 2 squared, and then plus 1/2. And then we'll take, this is just 10 divided by 32.2. And it's 0.75 squared. So we can actually find this value. I did it before, so I have that written over to the side. I didn't pick very large number for this, so it's actually not going to be much. 60, 32.2 divided, 2 divided, 0.375 squared, and multiply that. This is only like 0.131, so this one also is going to be pretty small, right? So 0.75, I'll square that first. Multiply by 10 divided by 32.2 divided by 2, and that's only like 0.08, so when you add them together you only get 0.2184, and these are in foot pounds, excuse me, pounds foot or foot pounds. Yeah, because we're using base units here, right? So we had slugs and we had feet per second, and you can see that a slug foot per second squared is a pound, but then we had feet squared over second squared because we had feet per second. We squared it, so that's where we have foot pounds. All right. Potential energy at state 1. All right. So the only thing that's changing, we said from this right here that we're going to start off with potential energy here. This is going to have potential energy, then it's going to have 0. This starts out with a 0 and it's going to have some. So it's only going to be the weight of A times its delta YA. Right? And it turns out that that's going to be delta SA times the sine of theta. Right? So it's actually how far this thing has moved up, but remember we're saying it's going to move down 3 feet, so the amount of distance it has traveled, it only matters the y distance it is traveling. Hopefully that makes sense what I've just said. So anyway, it's 60 pounds times 3 feet times the sine of 75 degrees. Right, 3 times 60 times. All right. So it starts out with 173.9 foot-pounds of energy. And this is really the thing that's driving it, right? So it has a lot of potential energy to start with, and then it's going to finish with none at A, but B's is going to increase. It starts out with none because we coined out the datum, and it moves upwards. Where's it going to go? Well, some of it's going to go away to friction, because we have this next guy right here. We have to look. We say U1 to 2. The only external forces that are acting on this are friction, and they're negative. Why is it negative, you ask? Because, well, for one concept we could have of this is that energy is being robbed from the system by way of friction. Friction energy is being dissipated into heat and noise and what have you, but it's being taken away from the system between states 1 and 2. We could also see that the motion is in the opposite direction of the friction force. So motion is going that way, friction force is coming this way, and therefore it's going to be a negative number. And that's going to be it's only the portion of the force that's in line with the motion, but in this case they are in line with each other, right? The delta SA and the friction force, that force times the distance that it moves through. So we have a negative 3.106, and it's moved 3 feet. So that's force times distance right there, or 3. Where did I get that again? 106 times 3, and so it's going to be 9. Oh, make sure I make it negative. Remind myself. Minus. And I guess I'll write it as a number, don't need the parentheses. 9.318 foot-pounds. All right, so the kinetic energy at state 2, all right, so we're just going to the next one. Kinetic energy at state 2 is going to be 1/2 ma VA2 squared plus 1/2 mb VB2 squared. All right, so we'll write a lot of this out, but we don't know the velocity. So what we're trying to solve for. Now we're asked, the question only asks for A. So for this one, we'll keep it VA2 squared. But this other one, it's a good strategy just to, after we get this done, it's a good strategy to put this in terms of VA. So this is VA2 divided by 2 squared. So let's go and put all those numbers together right there. It's a convenient thing to do, I think. Get it out of the way. So that's going to be 1/2 squared, 0.5 squared, times 10 divided by 32.2 divided by 2. Right? It's a pretty small number. And then we're going to have 60 divided by 32.2 and divided by 2. I'm going to add them together. And I got something different this time than I got last time, so I'm a little concerned. Should I be? Oh, I made a mistake. This is why I made a mistake. Maybe I was better to write this out over here, right? We know that VB is equal to 2. That would have been a bad mistake, but I caught it. All right, that should be VB is equal to 2, not 1/2. All right, so let me do this again. So that's going to be 4, 2 squared, 4 divided by 2 times 10. All right, and this is going to be 60 divided by 32.2 divided by 2, and add them together. Okay, got it. 1.553 VA2 squared. And then the last one, PE2. And as we kind of predicted, this one started out at 0, it's going to be end, and it's going to move up right there twice the amount that A has gone down. Did I do that correctly before? I'm double checking if I did that correctly. I think it's going to be okay. Yeah, it's going to go up 6. All right. If this thing, yeah, so it's YB is going to be 2 times SA. SA is 3 feet, so this is actually moving 6 feet right there. So we have, for the potential energy, we have the weight of B is going to move delta YB, which is going to be delta 2 times delta SA, or 10 pounds times 2 times 3, or 60, right? How did I do on that? Yes. And they're going to be foot-pounds. Okay, so I've gone through one of these at a time. Now let's go back and put all these into the original equation, right? The original equation was the kinetic energy, 0.2184, and that's quite small compared to the rest of the stuff, but that's one of the reasons why I think it's good to calculate the things out separately, so we put them in a list. And 173.9, that's where most of the driving energy comes from. The movement of this thing comes from potential energy change. Then we have a minus 9.318, right? So it didn't change. This didn't rob too much from it. The eventual kinetic energy is going to be right here, and then the potential energy right here, right? So it's going to increase some potential energy, but it's going to rob some of the potential energy that was actually driving this. But if we go VA2, so I'll take my 2.2184, which doesn't do much with my 173.9, but we'll still add it in there. We'll subtract out the 9.318. It's robbing energy from the system. 60 is at the end, so I have to subtract him. So I get 104.8 on the left-hand side, and I want to divide it by 1.553. And now we want to take the square root, and we end up with 8.215 feet per second. And so that's the answer. And did it ask me for the velocity, or did it ask me for the speed? Determine the speed. Okay, so they only asked for the speed, so we don't have to write down, make it into a vector, right? So the answer is VA2 is equal to 8.22 feet per second. And we're done. 22 minutes later.